Right, good evening everyone. Welcome to another introduction to astronomy. Let's start tonight with a launch.
Minus 15 seconds and counting.
And here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. And liftoff. Liftoff of Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Engine chamber pressures are nominal.
See that the chamber pressures are nominal from here. All 27 Merlin engines look great.
Rocket beginning to roll. Putting down 5.1 million pounds of thrust. Coming up, they're going to back off those.
Well, that was the launch in October of NASA's Europa Clipper mission. And you've got to ask yourself, why is NASA spending $5 billion to travel 2.9 billion kilometers over 5.5 years for a 4.5-year mission on a moon in the outer cold regions of the solar system? It's got something to do, the answer is it's got something to do with humanity's search for life beyond Earth. And which, referring to conditions that life needs, it needs these three conditions. It needs liquid water to dissolve nutrients for life, to transport chemicals, to support metabolism, to allow cells to get rid of their waste. You need compounds and chemistry for life. That's to make and assemble the building blocks for life. That's proteins, DNA strands, cell lipid membranes. You need all of those. You need some form of energy, whether it be in the form of photosynthesis or whether it be in the form of heat, to drive chemical reactions, to allow cells to process and metabolize, to allow them to grow and reproduce. And it just so happens that Europa may have those conditions, essential conditions for life, which raises the next question. Can and does Europa support life? And that's why NASA is spending $5.2 billion to travel 2.9 billion kilometers over 5.5 years for a 4.5-year mission at the outer regions of the solar system. And that's why tonight's talk is titled NASA's Europa Clipper Mission, the search for conditions of life. So I've split it into these 5 main chapters, if you will, here. So we're going to, first of all, we'll have a look about where is Europa and what is Europa. We'll then talk about what's special about Europa that's got NASA's interest, how to get there, and once you're there, what are you going to do? We're going to talk about the flybys the craft is going to do and some of the science they will perform, and then we'll wrap up with a summary. So let's talk first, Europa. Where and what is Europa? This is a not-to-scale drawing of the planets of the solar system. Here's your sun here, here's your 4 inner terrestrial planets, and there's your outer gas and ice giants further up there. And Jupiter is the 5th planet out. Now, putting that in perspective, Jupiter is 5 times the distance from the sun as the Earth is from the sun. So if my pinky was the sun and my thumb is the Earth, Jupiter would be sitting 2, 3, 4, 5. Jupiter would be sitting out here. If that was the sun, that was Earth, Jupiter would be out here. So it's quite some distance out. The average distance from Earth to Jupiter is over 700 million kilometers. Quite some distance. So it's a long way. It's well out of the habitable zone where you get liquid water, where the temperature is just right for surface liquid water. It's extremely cold, where in those outer regions of the solar system around Jupiter, you only receive 4% of the sunlight that we receive here on Earth. Just put it in perspective how cold and dim it is out there. So Jupiter has about 95 moons. All of them, bar 4, are all used, as Jonathan spoke last month, probably captured asteroids that are just very small and random sort of orbits. But there are 4 moons that stick out: Io, Europa, Ganymede, and Callisto. And size-wise, they're all comparable with the size of our moon, which I'll show you very shortly. Europa's the second one out here. These ones are much larger than the other smaller captured asteroid moons. They probably formed from some sort of a circumplanetary disk. When Jupiter formed, they probably had a disk around, and these 4 moons probably formed in that disk to explain how they're all in line like that. So you'll see here, yeah, Europa is slightly smaller than our moon. Let's just bring it up here. So there's your 4 moons with our moon here, and you can see Europa. To give you an idea, Earth's moon's across is about 3,500 kilometres across. Europa's about 3,100, so it's just smaller. Keep that in perspective as we start talking about some figures and facts and about it. It's just a little bit smaller than our moon, but comparable. So that's what Europa is and where it is. So yeah, what's so special about Europa? Most of the images and the data that we have on Europa to date are all from the Galileo spacecraft, when it was most active in the late 1990s. So the point of this mission is to go there and get more precise data for a dedicated mission. Galileo was primarily looking at Jupiter and had bits of looks at the moon at the same time. It's piqued our interest, which I'll explain shortly why. So NASA's decided it wants a specific dedicated mission with gather precise data on Europa, hence the Europa Clipper mission. From Galileo's data, there's good evidence, which we'll be talking about. There's evidence for a global, deep, salty ocean. So instead of just patches of oceans like Earth, but an entire globe, surrounding the entire globe of a deep, salty ocean. Just below the icy surface, they suspect there's hydrothermal vents of warm water coming up from the bottom, and that's providing energy and possible ingredients ideal for microbial life. That, in a nutshell, is what's got NASA's interest. Just to give you an idea of the dimensions, this ice that we got here, they think the ice is roughly about 22 kilometres thick. 22 kilometres. You know how thick the ice is, the ice sheets on Earth? The thickest ice sheets on Earth around the polar regions, 5 kilometres deep. 22. And here we've got a body that's smaller than our moon. Ocean, suspect, is about up to 150 kilometres deep. The deepest parts of the oceans on Earth, 10 kilometres. You're talking 150 here. What if I told you that this celestial body, slightly smaller than our moon, has more liquid water, ocean water on it, than twice the amount on Earth? The entire Earth, all its seas and oceans and lakes, it's got over twice that on this body that's smaller than Earth. Wow. Furthermore, there's evidence which we'll talk about is these hydrothermal vents. They suspect, we're going to talk about why they suspect that, but they suspect there's hydrothermal vents going up here too, providing warm water, heat and nutrients. So you can see why it's got NASA's interest. So what is the evidence? You might say, well, what is the evidence from Galileo? What is the evidence that all these things are going on there? And there's some surface features, tidal features and magnetic field line features, each of which we will discuss. So let's talk about 5 surface features. First of all, first impressions, when you just look here at Europa, let's just blow it up here. I love that image. So that's an image of the Galileo spacecraft. What's the first thing you notice? The surface is smooth, isn't it? Very smooth surface, and that tells you it's sort of probably icy. It's the smoothest surface in the solar system. It's Europa, surface of Europa, the smoothest surface. The other thing, it's white, isn't it? It's background colour of white. That tells you it's likely water ice. The other thing that you notice on first impressions, notice all these blotchy, brown, reddish, blotchy areas here. What's going on here? We'll talk about those shortly, but in a nutshell, they suspect that that is probably salts, organic and other compounds that have been turned that colour from radiation from Jupiter. So we'll be talking about that. So already, you think, wow, this is interesting. Or maybe I'm just get excited very easy, but don't everyone do a crowd brush at once. It's okay. So I find that quite exciting. And the other little thing of these, look at these little crisscross regions across here too. You might say, well, that's interesting. Where have I seen those before? That is the pattern that you get of tectonic activity underneath ice, where there's water moving around under ice. You'll get that sort of pattern of crisscrossing going on. And the other thing you notice here, or more to the point, the lack of, there's no crater activity, is there, around here? And as you may be aware, that where you see a surface that's not cratered, that indicates it's a very young surface. It's geologically active, that gets turned over. They think the surface is only about 60 million years old, which is the blink of an eyelid, considering it's about 4.6 billion years old, the actual moon. Yeah, very exciting. Well, I get excited anyway. That's just your first impressions looking at it. What do you see? So let's talk about these surfaces now. The first one, is chaos terrain. I'm going to come over here. It's probably easier for me to talk. Chaos terrain. And that's what it looks like there. That is the terrain of Europa. And you'll see it's all jumbled up, but also you see these big sheets of ice that have all been disturbed. Some of them have been rotated, some of them have been tilted upwards. They've all twisted and distorted fragments of ice. Then you get areas here like these huge big domes, you get pits in here, you get ridges, and to put all those in perspective, they are up to 200 meters high. The ridges, the domes, and the pits for their depth, you're talking about 200 meters. So there's really quite some big dips and some big domes going on there as well. And that really does point. Ice does not do that unless you've got something moving underneath it, which is water. Water is moving around and acting on the ice like they do with tectonic plates. That's the most likely explanation for that. Second thing is these linear that we saw, these crisscrossing lines. And these here are ridges and cracks. Probably, once again, that same pattern you see on Earth underneath ice, where you've got tectonic activity going on, such as water moving around and so on. So that's another good, strong evidence that there's underneath there, that there's ice plates are getting moved around. Furthermore, the brownness, as we've talked about, is very strongly that there's salts coming to the surface as well. So water is coming up from underneath as well, creating these cracks. And that's what the brown colouring is, the ridges and the cracks, where salts and organic compounds are coming up underneath it and are getting to turn that brown colour by radiation. Now, you might think, well, how do the cracks form? It'd be warm water rising up through the cracks to deposit those salts and organic compounds. The ridges, as I've mentioned, along here, they're up to 200 metres high. We're going to have a look inside one in a minute. And the cracks and canyons, these just look like, some of them just look like lines, but you'll see here, these are 10 to 50 kilometres wide. That's an artist's impression, what it would be like inside one of these little cracks or lines that you see here. And so what's happened is warm water's come up through here, and the cracks got wider and wider and wider, and then it's just frozen over. But they can be anywhere from 10 to 50 metres across, and these sort of ridges here can be up to 200 metres high. So it's quite an exciting place. The crisscross patterns, as I've mentioned, very similar to Earth's tectonic spreading crust and ice, that you see all these crisscrossing active going on here. Then, as we've talked about, you get all these big brown sort of blotchy areas here, and that's highly indicative of salts and organic compounds coming up from the ocean below. There it is there. So the Galileo did spectroscopy on them, and it showed there was, amongst the water ice, there were your salts, possible organic compounds, all coming up, and that implies that that ocean, of course, is salty. That's what that's implying. You're getting salts coming up to the surface, they're picking them up on spectroscopy, they're turning brown from radiation, and they suspect there's probably organic compounds in there as well. So not only does that tell you that the ocean is salty, the fact that there's a lot of organic and other compounds in there with minerals in suggests that the ocean is also communicating and interacting with the ocean bed at the bottom and below the ocean bed as well, which is, it also the fact that the water is coming up and melting ice suggests that it's warm. So all this evidence is pointing to water, warm salty water with minerals and compounds that are probably coming up from the bedrock, but also underneath the bedrock as well. It's coming up, and we all know that in these conditions here, life thrives on Earth in these sort of conditions. Here's another an artist's conception of what it would be like on the surface of Europa, looking back towards Jupiter. So you can see it's sort of relatively smooth. It's just got these little rocks and stuff here, but it's mainly ice and all this red discoloration, reddish brown discoloration here as well. So it just gives you an idea what they suspect it would be like. Now, there's plumes of water vapour coming up. So this is an image taken from the Hubble Space Telescope, where they've seen plumes of water vapour going up to 200 kilometres up into the air, shooting up. What does that tell you? It tells you the water's under pressure. What raises pressure a lot is warmth as well. So there's warm water shooting up these big plumes of water that are hopefully will still be full of salts and organic compounds as well. And the importance of these, of course, is you don't have to go and land on Europa to drill to see what's going on in the oceans. You just have to fly through those, and that's what they're hoping to do. And it's like going to the moon. Where do you land? You land beside a crater because nature's already done the digging for you. It's the same here. Nature's already doing the drilling for you. And drilling. You'd never drill through 22 kilometres of ice. So nature's doing it for you. Obviously the water is under pressure, which indicates, yep, there's heat and energy underneath there that's driving that. So Europa, Galileo spacecraft got within about 200 kilometres of the surface of Europa. They're hoping to get well inside that, getting down to about 25 kilometres, well within those plumes. They hope to travel through those plumes with Europa. That's what an artist's impression is like, is that you've got your ice surface here, you've got warm water that's finding its way up, the water's moving around, it's got tectonic movements, little cracks are forming, you've got warm water that's going up through those little cracks and melting it as it goes, it's all under pressure, and you're getting plumes coming up like that. So that's what they think is most likely causing the plumes. They also think there may well be some little encased lakes, if you will, enclosed in the ice as well, that then also with under pressure, particularly when you get the tectonic activity of plates moving around, creates a bit of pressure in there too, and they would come up as plumes as well. So that's what they think is most likely behind the plumes. And then as I mentioned before, lack of impact craters. So it is the smoothest surface in the solar system all over. And that's indicative that the surface is renewing itself. An old surface like the moon, of a place that hasn't got an atmosphere, so like Mercury and the moon, that old bodies that don't have atmospheres, you see them, they're all heavily cratered. And it's only, we don't have lots of craters on Earth because we've got an atmosphere, and of course we've got geological activity that overrides them, it wipes them out. And when you see a smooth surface like that, that says it's a very young surface. They estimate it by the crater counts, and they estimate it's less than 60 million years, which geologically is a blink of the eyelid. Okay, so that's 5 surface features that have been identified at Galileo that says, whoa, we've got some interesting features going on here. We've got a global ocean underneath that ice. We've got salts in there, we've got organic compounds in there, we've got pressure going on there, we've got water that's moving, we've probably got hydrothermal vents as well. We need to investigate because they are all the conditions for life. So let's go and look at some of the tidal features that provide evidence as well. And at the end of the day, you've got these 4 moons lined up next to the largest planet in the solar system. And in response to the huge gravitational forces that Jupiter applies upon its moon, has a strong gravitational pull. And we've all seen what the effects of that, what the moon and the Earth has. We get the water tides go up and down, but they only go up and down by a metre or two, don't they? And that's with the oceans, and the solid land does not go up much at all. just going to go back a sec. Is that 30 grams? Yeah, no, it is. Okay. So, yeah, that's it there. So Jupiter has quite a strong influence on Europa, where you can see it gets the tidal forces stretch and stretch and pull and stretch on Europa. Yeah, the ice moves up to 30 meters. So the ice tides go up 30 meters on Europa. You think about that, 30 meters, and that's solid ice. You'd find that really, really difficult to explain without the concept of there's water underneath that ice. It cannot be solid. You cannot get a solid surface going up and down 30 meters. That's highly indicative of, yep, there's a huge layer of liquid ice, liquid water under the ice. It's just for that going on 30 meters. So that's surface features, the tidal features moving 30 meters. That's really suggesting there's a big, strong global ocean underneath. The other thing is magnetic field lines. You might think, what's all that about? Jupiter has very strong, powerful magnetic lines going right around the planet. It's a global magnetosphere, like Earth has. You might say, why does it have that? It's because it's got a solid metallic iron core, a large one, and it's rotating really quickly. Every 10 hours Jupiter rotates. So that generates really strong, powerful magnetic fields, second only to those around the Sun. And because of that, you get these belts of trapped charged particles, or radiation, much like the Van Allen belts you get around Earth, except they're far more intense, but they're around Jupiter. And guess what? Europa orbits Jupiter constantly through those belts, the equivalent of the Van Allen belts. So it's exposed to a lot of radiation. So Galileo was able, with its magnetometer, was able to assess and analyse the magnetic fields coming from around Jupiter, and all looked good. But around Europa, there was a significant disturbance, a disruption of those magnetic field lines from Jupiter, suggesting that in response to Jupiter's magnetic field lines, Europa was busy generating its own. It was inducing Europa to form its own magnetic field lines. And which really points towards what would do that? An ocean with ions, with salty ions. A salty ocean just getting sloshed around and around underneath the surface. That would be responsible for it as well. So that's Europa generates its own magnetic field lines around it in response to Jupiter's. Once again, more evidence, highly suggestive there's a salty ocean around the entire moon underneath that ice. So these are your magnetic field lines. So it's these here. So that's all the evidence, because you think, gosh, we haven't, they've only sent one spacecraft. That's what Galileo's done. It's gathered all those evidence there that really points to a global, warm, salty subsurface ocean that's interacting with the rocks and what's below the rocks as well. It's interacting with its with underneath the ocean. And that's, in a summary, what they suspect's going on. So you've got 22 kilometres of ice, up to 150 kilometres of ocean, with these hydrothermal vents with heat is coming up from below, and it's bringing up minerals and salts as well. And as I mentioned earlier, that is just, life just thrives on Earth in those conditions we know now. Life on Earth may well have got started under these conditions. There's a lot of evidence pointing towards, quite possibly, hydrothermal vents at the bottom of oceans is how life got started on Earth. A lot of evidence and thinking along those lines. And here we've got it sitting in Europa. So that further then is inferring there's some sort of heat source going on. You think, well, what's driving this? We're out in the cold regions of the solar system, only exposed to 4% of the radiation from the sun that we get on Earth. So what's creating this ocean? What's providing the heat for that? What's providing the heat for this, for these hydrothermal vents and all the tectonic activity? What's going on so far cold out in the solar system? And the general idea is that it's very, very hot in the internal regions of Europa, and it's starting to rise up. Well, it's been rising up through there. So what powers these tidal and geological processes? There's two things. It's tidal locking with Jupiter and what we call orbital resonance. Let's have a look at tidal locking for starters. Okay, so here you've got this big Lovely big planet, Jupiter here, the biggest in the solar system. Then you've got these 4 moons all lined up here. Yep. Now Jupiter's large mass is 318 times the mass of Earth, and that puts a lot of significant tidal forces on these Galileo moons here, such that these moons are all tidally locked. That means they rotate at exactly the same rate at which they orbit Jupiter. Like our moon does exactly the same, so the same side is always facing Jupiter and always facing away. So that the moons are tidally locked, so which means they rotate at that same rate they orbit Jupiter, and that creates a constant pulling force on these moons. And as I mentioned earlier, 30-meter bulges on Europa just because of the tidal pull of Jupiter on it. Now, orbital resonance is next. I think Jonathan spoke about this last month, so it's good to review it. Due to these moons all being relatively close, so it's more applicable to these 3. Callisto hasn't quite joined in on this yet, but due to Io, Europa and Ganymede being reasonably close to one another and their mutual gravitational attraction, they all tug and have an influence on each other. So just as Jupiter pulls on them, they pull on each other as well. And that results in a regular lining up of their orbits, which I will have a look at now as illustrated. So first of all, we've got this nice diagram here, and you can see here, gravity drives orbits. So whenever you get like planets going around the sun and moons going around a planet, that the inner ones always go faster because it's gravity that drives the orbits. And of course, gravity is a lot stronger closer to the main source. So these ones always go closer. But you can imagine if they're out a little bit, the slower moon's going to be pulling the slower moon further out. It's going to be wanting a bit of a tug, wanting to pull this faster one back a little bit each time. This faster one's going to want to pull the slower one forward to join it. So whenever they get close to one another, they're always going to pull on each other to bring themselves in line irregularly. And they're also going to pull and stretch their orbits out a little bit to try and make elliptical sort of orbits. And in contrast to Jupiter, will always allow them to do a circular orbit. So there's already a lot of pulling and tugging from Jupiter and on themselves. And this illustrates the regular alignment that they do regularly. And you start here, here's Jupiter, Io, Europa and Ganymede. So this is after one orbit of Io, it's back to its original place. Europa's done half an orbit, so there's a nice alignment there. Io does 2 orbits. Europa has completed 1 orbit, back in line, and Ganymede has done half an orbit, but once again, it's in line. So they're all having an influence on each other, and after 4 Io orbits, it's been around 4 times, Europa's been around twice, and Ganymede once. Once again, they're all lined up. So it's a regular lining up of the orbit, and that's called an orbital resonance. And it's because they're reasonably close together, and they're gravitationally mutually attracted towards one another. So as they get close to one another, they try and pull each other together, such that with time, they develop this regular alignment. Now, here's a little video to show that. Here you go, there's an alignment there. There's Io and Europa lined up nicely. There they are, all lined up again. There's Europa and Io lined up, and we'll do one more with Ganymede. There they are, they're all lined up again. So they do that on a regular basis. So it's that repeated and opposing the gravitational tug between Jupiter and the moons within themselves that causes an ongoing stretching and squeezing off their interiors. Which means the interiors are just going to get squeezed that way, squashed, squeezed, stretched out, and it generates a lot of internal friction and heat. And a good analogy of that is your paper clip, a bit of metal paper clip. It's cold, you get a bit of paper clip and just bend it backwards and forwards, that gets hot. It's the same, exactly the same principle. You get something solid, like a big massive rock with the center of one of these moons, and you stretch it and squeeze it and all these opposing forces, it gets hot, it generates internal friction. And that is what's driving the heat in these moons. And there you go. That's what's driving all this heat going on here, which comes up through the oceans, hydrothermal vents, and of course gets the water moving around and creates all this geological activity, tectonic movement. So that's what makes Europa so special. You can see now why NASA is really, really interested to go and explore it. Now the next thing is how to get there, and I see there's a nice little article in the journal this week on this. So they launched it off, first of all, with a nice powerful rocket. It was actually this one right here. They were going to use NASA's Space Launch System, which would have put it up and gone directly to the moon, but NASA's had problems with it and it wasn't ready. So they used the SpaceX's Falcon Heavy rocket, which has 27 Merlin rockets, which has the same power of 18 747 jumbo jets, full power. It's the same power in one of these rockets, this Falcon Heavy here. So they launched it off, and that was launched, as it said before, the 14th of October. We're going to go into this in a little bit more detail, but it actually didn't go straight out to Jupiter. It did a course, it went around Mars, and then came around, back Earth again. It just did Mars just this week, and then it's going to come around Earth. We're going to go through this and around to Jupiter to do what we call some gravitational flybys of planets, which is a very efficient way without carrying fuel, but you get extra energy and speed. So we'll talk about that. So it was launched on the 14th of October, which we saw at the very start. This week, it flew around Mars. Then it'll go around Earth on December the 3rd in 2026, and then on to Jupiter. Now here's just a little video clip of that. So you've got the sun in the middle, which is yellow. You've got Earth's orbit, which is blue. You've got Mars' orbit here, which is that light yellow, and Jupiter's around here. And you've got magenta for the probe, for the spacecraft. We'll have a look how it goes. Here's a readout of how fast it's going. Your dates at the top. It's gone out. Gone back around Mars and then Earth, and then heads out to Jupiter. That's why, because you probably picked up when I talked about that Jupiter, you're talking sort of, it's averaged about 700 million kilometres away, but it travelled 2.9 billion. That's why it didn't go in a straight line. So it takes 5.5 years to get to Jupiter for its 4.5-year mission, which will be in 2034, September the 3rd. Now, the whole thing of gravitational assists is what's going on there. It's when you do a flyby around a planet and you get a booster, you can alter your velocity, your speed, and your position as well, which we'll talk about. But here's just a lovely little Voyager 1 as it went around Jupiter and Saturn. You can see the speed down here. You see it coming for about 13, 14 kilometres per second, bumped up to 23 kilometres per second. But notice the change in direction as well. So if you calculate it right, you can increase your velocity and reposition yourself as well, your direction of travel. So that's what Voyager 1 did. So yeah, what's going on with these, and you can speed a craft up or you can slow it down with these gravitational flybys. And the idea, because it's counterintuitive, you intuitively think, oh, if there's your big planet here in your spacecraft, that you're getting drawn into it by the pull of the gravity, that's speeding you up. But that's not so. Well, that does happen, but that's not the reason for it. Because if it's because of that, because the gravity's pulling you in, sooner or later you've got to move on from that planet too, and that's going to be pulling you back. What's going on? If you get in close enough, you become within the gravitational influence of that planet, and you're actually stealing some of its orbital speed. So the planet's going around the sun, and it's moving around like that. Usually they're traveling at many kilometers per second. Your spacecraft comes in here, and it gets drawn in, and it actually transfers some of the velocity of the orbital velocity of the planet, and then you head on back on your way again. So it's part of the conservation of angular momentum, but the bottom line is you're taking away from the planet, stealing sum of its angular momentum, or its mass times velocity is momentum. So its velocity, its orbital velocity, and of course it's been conserved. You're within its gravitational influence. The spacecraft's got a tiny little wee mass, so it takes some of the speed away from that. But the planet doesn't notice it, doesn't miss it one little bit. So that's what's going on. Now that's to speed up. If the planet's going around, say, this direction, and you come in from that direction, you're going to speed up. If you want to brake and slow your craft down, you come in from the other way. If that's the planet, you come in from this direction, and you'll actually slow down. And it's braking, and that's when they go to the missions to Mercury and to the Sun. They brake. They go around Venus, and they'll go around Earth and stuff, and they'll slow themselves down by doing a gravitational flyby, but in the opposite direction of the orbit. So that's what's going on with gravitational flybys. So they use those, very, very important. So that's how to get there. What you're going to do once you get there, we'll talk about the flybys and then a little bit about the science. Okay, so the flybys. So once you get there, they don't just go there and go and orbit around Europa for two reasons. The big reason is that intense radiation we talked about. That would fry the spacecraft and all its sensitive electronics very, very quickly, within hours. So, in fact, the intensity of the radiation on the surface of Europa is so intense, you would not survive 24 hours unprotected. You wouldn't, even I think with modern day protection. To put it in perspective, remember when we talked about astronauts going to Mars and astronauts, their career, NASA puts a career limit on 600 millisieverts, a cumulative amount of exposure. They could use the unit called sieverts. It allows for the amount of damage to various organs from various types and intensity of radiation. And astronauts are capped at a cumulative of 600 millisieverts, so 0.6 of a sievert for the entire career. If they hit that, bang, no more space travel, thanks very much. On the surface of Europa, in 24 hours, you'd be exposed to 5.4 sieverts, not millisieverts, sieverts. In other words, 5,400 millisieverts in 24 hours. That's what you'd be exposed to. You'd be dead. So the radiation exposure is really intense. So when they fly through that, of course, they would naturally fry all their equipment. And they get around that by twofold. One is it's an aluminium titanium, and they literally call it a vault. They keep all the instruments in a vault on the spacecraft to help protect it, but also they only want to stay in Europa's orbit for a minimum amount of time before they do a wide sweep around Europa, just give all the instruments a break from it all and come back in again. And the second reason they do that, let's just bring up these slides here. I'm going to show you this. But the second reason they do these wide sweeps is transmitting data back to Earth. They gather data when they go around Europa quicker than they can transfer it back to Earth. You know what the bottleneck is? It's the receiving stations on Earth is the bottleneck. The craft is happy to send it, but we can't receive it quick enough. So they use that downtime to transmit the data back to Earth as well. So let's have a look here. So you've got in the middle here, you've got Jupiter. In red, you've got the orbit of Io. And that light blue there, you've got the orbit of Europa. And there's Callisto, the outer moon there. Here we go. No, sorry, it's me. Let's just do that again. Here we go. You click it, then I just got to wait, be patient. So, here we go. So here it's going around, big flyby, huge elongated elliptical orbit, way out there. Does 49 flybys in total over that 4.5 years. That's to minimise radiation exposure and transfer data. And notice the orientation or the precession of the orbit of the flybys changes too. Because what I tell you about Europa, it's tidally locked. So if you did the same orbits, you'd only see the same part of it the whole time. You wouldn't see the other side. So they do different orientations of the orbits. They hoped about it, map out in those 4.5 years, about 80% of the surface of Europa. So there you go, tighter and tighter and tighter. Eventually, I think the plan is to crash it into Ganymede away from Europa. They do not want to crash in Europa because it'll contaminate Europa's conditions. So there you go. That's the flybys they're going to do when they get there. Now the instruments. So there's the instruments and the science. They've really packed it to the hilt. So there's 9 scientific instruments on the craft. Let's have a look at what they're all for. So there's 2 imaging systems in the visual and the infrared, 2 light spectroscopies in the visual and the ultraviolet, 2 magnetometers to measure magnetic field lines, 1 radar that's to look through the ice, 1 mass spectroscope to see what's going through, what's flying through up from these plumes, and a dust analyzer. So let's have a look at them. So your imaging systems, the first one here is invisible light, and for your technical minded people, you've got a high resolution wide angle and you've got a high resolution narrow angle. With a wide angle camera, 48 by 24 degrees, resolution 11 meters resolution from 50 meters up. That's pretty good. And then the narrow angle camera, 1/2 meter from 50 kilometers up, and they hope to get it within 25 kilometers off it. So they're hopefully about to see to to a 1/4 of a meter in detail. That's incredible, huge resolution. The thermal imaging system, once again, so that's imaging, but in the infrared, and that's really to look into geological activity where there's warmth and heat going on. So they hope to detect areas that are geologically active by going into the mid and far infrared with high resolution. The spectroscope, there's 2 light spectroscopes that they will look at identifying the distribution, or looking at the ice, but looking at the distribution, what salts are there, what compounds are there, what organic compounds are there, and their distribution, how are they distributed around, and the various minerals and well. And they'll get a wealth of information from that as well. The ultraviolet spectrograph, that will detect really very small, if there's small hot plumes coming up that you can't see with visual wavelengths or just too small, the ultraviolet spectrograph will be able to detect that, and it has a better idea of studying the composition and the dynamics of what's going on in what they call the exosphere. That's part of the atmosphere that the plumes are adding to. 2 magnetometers. And the idea behind that is to assess the magnetic fields that are going around it, the ones from Jupiter, but also the ones being generated by Europa as well. And of course, that will give them a lot of information, once again, about the depth of the ocean, how salty it is, distribution of the salt, and so on, through measuring its magnetic field lines. So what they've done, they've also got one here called the plasma instrument, and that is designed to assess the amount of charged particles and the directions they're going, and from there working out out of the magnetic fields they're finding, working out, separating what's due to the plasma that's floating around there within those radiation belts through which Europa's going, what radiation around Europa's from that, and what radiation, or what magnetic field lines rather, is coming from actually inside the oceans. So they'll do the first one to assess the whole field, the magnetic field, the nature of those magnetic field lines. They use the plasma instrument to work out what's due to the plasma in the belts, radiation belts, and they can deduce what component of that is from the oceans, the salty oceans.
Excuse me?
Yeah.
Do we have any evidence of how salty the water is?
That's the purpose of the salinity, how salty it is. We don't, and that's what's all circumstantial evidence from Galileo. Good question. Yeah, Galileo has just provided all these clues and features and evidence, and it is the job of this mission, highly dedicated, precise measurements to do exactly that. So, good question. Yeah.
My second part is, do you have any idea how, can life exist, and how salty can water be before life can't exist?
I can't tell you the top of my head. I'm sure there is a figure to that, and I'm sure that they've got constraints. I did see a paper about the constraints of the salinity, but it's that through the strength of the magnet. I'm sure if you look it up, there will be papers on that. It's just not my field in terms of the salinity from the amount of magnetic field lines. But what you've highlighted is, that's the point of it, is to work out the salinity, absolutely, and it'll give them an idea of the depth of the ocean as well. Yep.
Chris, can I jump in also?
Yes.
Is it safe to assume that it has a metallic core?
Oh, it'll probably have a rocky metallic core, like most terrestrial planets, just a very small one. from there.
Something that helps assist in generating this magnetic field.
Oh, they think the magnetic field, it'll be a rocky core, but it will not probably have a big chunky iron core like Earth or anything like that. No, it's from the oceans. And they suspect that the magnetic fields that they can see around the ice giants, Neptune and Uranus, are probably exactly the same. Some salty water in there sloshing around.
Surface regeneration is from the thermal vents that's recoating the surface.
Yes, with tectonic plates, yeah, exactly. The surface might get a crater, but with time, that bit of ice gets turned over or distorted or straightened out again through tectonic activity, driven by the heat from below. Correct, absolutely. But the magnetic field lines are thought due to the salty oceans, yep. Then you've got the ice penetrating radii that's going to get a better idea. So those are only estimates of the 20, when I say 22 kilograms, it's an estimate. This will get a better idea. And is it uniform? Is it not uniform? And so on. So they will get a much, over those 4.5 years, get an idea of the icy crust, how thick it is, and if it's uniform or not. It will also try and look for and detect any of these pockets of ice, these encapsulated little lakes and so on. So you can see the research, what the instruments they've packed on board, they're going to get a wealth of information over these 4.5 years. It's got a mass spectrometer. So you might say, well, does it have much of an atmosphere? It has a very tenuous, very thin, tenuous atmosphere. You know what it's primarily made of? Oxygen. Why? Is that the radiation from Jupiter creates oxygen, reacts with a lot of the compounds on the surface and creates oxygen. So that's interesting. You might think that's the other thing is about what I'll mention now is that you might think, well, this radiation, how could life survive all that radiation? What's one of the best protectors, as we talked about with radiation with astronauts? Water. Just hydrogen is your best protector. You've got this big, thick, 22-kilometre ice sheet over the top. That gives you plenty of protection for life underneath. And ironically, the radiation is pleasantly a double-edged sword. There's another side to the radiation. It helps to create oxygen, a little bit of oxygen in the atmosphere, but then in turn it helps to oxidize, create oxidants, which life would then use, and like hydrogen peroxide and so on, which life would really like that. And a lot of these compounds that are favourable for life, that would be good fuel and nutrient for life, is being created on the surface, which then goes down into these oceans below because of the radiation. Yeah.
Any evidence of carbon?
They will find a lot of those compounds will be, those organic compounds are carbon and hydrogen. That's what organic compounds are. So to answer your question, yeah, carbon, yep. Carbohydrons, hydrocarbons, yep. So it will also pick up any other surface material that's ejected into space as well from the plumes and so on. So that's the mass spectrometer. It also has a surface dust analyzer. So it's these lovely little cavities here with grills and filters on them, so they will collect any of the solids that's coming up as they fly through the plumes. It's also could pick up, if there's any bacteria, it'll pick up a bacterium molecule, so possibly some microbes it might be able to pick up, if there are any. Of course, this mission is not about looking for life, it's about looking for the conditions favourable for life. So, but if there happened to be a little bit of life, a single bacterial cell in an ice grain, it would be picked up in those plumes. And then, this is interesting too. So they can also tell the internal structure of what's going on inside the moon with the high gain radio antenna that signals back to Earth at radio frequencies. The craft itself and Earth will monitor it. And the craft's going to be going around, so you're going to get with the Doppler effect, you're going to get changes in the wavelength of the radio waves, but they'll look for any anomalies. If there's a denser area in Europa, a more dense area, a gravitational anomaly, the spacecraft will speed up a little bit, go past it, and then it'll slow down as it goes past. They will pick that up by studying the wavelength of the radio waves, so that the craft can do that and Earth will be doing that as well. So that's how they're able to see if there's any anomalies within the structure of Europa and its internal structure as well by the tidal forces. So how is it powered? Solar energy. You're talking only 4% of the solar radiation, but it's huge. The panels, size of you got two 18 square solar Vita panels, the size of the Statue of Liberty, rather. Yeah. So, and of course, when it's in the shade, it'll charge the batteries. So we'll have some batteries on as well, but primarily just two massive solar panels. And it's got some hydrogen engines for propulsion, like for its orbital burns and so on, to control its attitude and its orbital insertion. So yeah, look at the size of those panels. That accounts for the 4%. So that's what to do once you're there, the flybys and the science. So let's sum up. So the evidence to date, that's from the Galileo in the late 90s, suggests that Europa has conditions suitable for life, including a global, right round, subsurface underneath a nice healthy thick layer of ice, compounds for chemistry and hydrothermal sea vents that would provide energy and nutrients underneath, minerals and so on for life. So if there's one message you take away from tonight's talk, it is this. Clipper will investigate Europa's conditions for life in unprecedented detail. And that's why NASA is spending $5 billion to travel 2.5 billion kilometres over 5.5 years for a 4.5-year mission in the outer cold regions of the solar system. That is why. Thank you.
Thank you.
Any other questions around there? Yeah, sure.
What would we likely to see here on Earth, like televised? What kind of imaging?
Oh, it's all going to be, see Alex, it's all going to be raw data. We're not going to, it's going to be raw data.
So it'll be interpreted data.
Yes, correct, yeah. And of course, NASA will release some some of those images, the visual wavelength images, they will get released nice and early, but otherwise you're predominantly talking data that will take some time to pull apart and work through, yeah. Yeah.
Are the orbits of those moons,
yes,
are they all uniform, or are they?
There is some eccentricity to them because they try and pull it into eccentricity. So you've got Io, Europa, Ganymede and Callisto, they pulling on each other. Jupiter would, if left to its own device, would just have the nice circular, and Jupiter pulls them in evenly as they go around. So that's one pull on them. And to illustrate how strong that tidal pull is, Europa goes out 30 metres. But on the other side of the coin, you've got the moons each pulling and tugging on one another, which creates that orbital resonance, but also stretches them out when they do get in line, pulls them out a little bit outwards into a more eccentric or elliptical orbit. So it is slightly elliptical, and it's the tug between the two and the orbital resonance and just the tidal forces of Jupiter that are constantly pulling and stretching, causing the internal friction. Yeah. So they're not highly elliptical. Yeah, Tony.
Where's the 5 billion go?
Where does the 5 billion go? Yeah, good question, because people I love that question, because exactly, I remember when the astronauts, there was one of the team of astronauts came back from the moon, and some cheeky, reporter, still with his proverbial diapers on, said, "Oh, what a waste of money! You guys just spent all these millions of dollars going to the moon." And I think it was, and one of them turned around to one of the astronauts, turned around to the other two astronauts. Did you spend any money on the moon? No, I didn't spend any money. No, I didn't even take any money with me. No, it's all pumped back. It mobilised industry, education, science, technology, employs scientists, technicians. Absolutely. So your point is quite right. That $5 billion gets put back into a very healthy aspects, facets of the economy. It doesn't get spent anywhere else. So I think that's where your head. Where does it get spent into? Yeah, into the development and research. Look at the JPL. We'll see the technicians in the White Room and stuff all working on it. They're developing new technology for it and so on. Employing intelligent, healthy people to stimulate science, technology, and science.
Probably 20 years of employment there.
Yeah.
20 years of employment.
Yeah. Yep. So it stimulates, and all, of course, that filters through the whole economy. And that was JFK's when he said, we're going to go to the moon. And that was brilliant. It wasn't, it was about going to the moon for the Cold War, and sure, that was the point there. But more than that, he mobilised industry, technology. He inspired people. That got the US technologically just pushed them ahead. Engineering, science, technology, education. So that's a good question. That's where it all goes. Yeah.
I think you were implying that I'm wearing
Oh, that's funny. No, not at all. No, that's. But you asked the right question in terms of it, you're highlighting that no one spends a cent elsewhere. Yeah. Yep. Absolutely. So yeah.
Sorry. Just one clarification on the heat generation part of it with the tidal locking.
Yes.
So am I right in thinking that's only generated just that aspect of it? If there was just one moon, that's only generated because that would only be generated by the sort of elliptical nature of the orbit. It is entirely circular. If it's exactly circular, you wouldn't be stretching and squashing the moon.
It is because yeah, it's the conflicting forces that are going on, the opposing gravitational forces between Jupiter has its big tidal pull, and the other moon's putting it in orbital resonance that are pulling it.
Just one moon, it's just pulling it. It would just be pulling it to an ocean.
You wouldn't be getting that if there was only one moon. You wouldn't be getting that generation of heat if there was only one moon. Correct.
Except if it was elliptical orbit, then it's changing.
Yes, yeah, and then you'd have to have some.
The force would be changing.
Yeah, you'd have to have some big forces there sort of making that. But the key to it is that orbital resonance. That's opposing. So you've got opposing gravitational forces stretching and stretching.
The Earth's move would be causing some heating of the Earth, but that's because the Earth is rotating. So it causes the actual tides in the atmosphere, the ocean, even the rocks are moved around a bit. But yeah, you only get that because the Earth is spinning, and that means that it's not a fixed configuration like you're talking about.
Okay, cool. Yeah, thanks.
Yeah, down the back. So, how many Earth days? Oh, for Europa to completely do a rotation? Or Europa? Yeah. Okay, so how long does it take to go round, complete orbit? And look, I am unsure. It's probably a lot of astrophotographers will probably tell you that because they follow it through with you. I can't tell you off the top of my head. You probably Google it.
In line with the rotational speed of Jupiter.
It rotates. They rotate at the same speed they go around. I'm sure if you quickly looked up on your smartphone now, orbital period of Jupiter's moons. Of Europa, it would tell you. I can't tell you, so I don't want to put you wrong. Yeah, Tom.
I realise we don't really know why it's got so much water, but is there a theory why Europa?
Yes, so there's theory why Europa's got so much water. Well, interesting enough, because Earth doesn't, it's deceiving. We think of Earth's got a lot of water, but it probably doesn't in the big picture because a lot of those outer moons have much more water. Titan is suspected to have 10 times as much water on Earth. Where does the water come from? You're talking out in the ice. One possible source, there's a few potential sources, about 3 of them. One is from the solar nebula. 2 is from just minerals within, when the body forms, when the celestial body forms, and other delivered by icy objects such as asteroids from the outer asteroid belt and comets. Of course, the further you go out, the more you're exposed to all those icy parts of the solar system with your comets and stuff. They're going to cop a lot more comet collisions. So I would say probably most of that. They will no doubt analyse that. How do they know where Earth's water come from? Is they measure the isotope ratios of the hydrogen, with H2O, with how much is heavy water and how much is deuterium versus normal hydrogen isotope. And they would compare the ratios with those of comets and with the outer asteroids. And that's where they said most of the extrinsic water derived on Earth probably came from some carbonaceous asteroids in the outer part of the asteroid belt, not comets. So it'll be interesting if they go through one of those plumes and get some water, and I don't know if they can or not, but have a look at the different isotopes and they might be able to match it up. But just me wildly speculating right now on the spot, I would have thought it's those outer regions of the solar system was exposed to a lot of frozen ice early on, from comets and so on colliding with them.
So Chris, here's a question. How does water come to exist?
H2O.
Obviously hydrogen, right, and oxygen, right,
Yep.
combined. But I mean, if we have a massive explosion and we're creating this leftover hydrogen and oxygen, right, is produced from it, how do they come to exist as a molecule?
Water vapour. Oh,
In space, how does that come
water
to
vapours in space.
Yeah, but how does water vapour come to exist?
Oh, okay, because oxygen's highly reactive.
Right.
Hydrogen is the most commonest element in the universe. Your next one is helium, and of course helium's inert. It's just good for party balloons, actually, and MRI scans, coolant. And oxygen. Oxygen is the third. So hydrogen and oxygen are the two most commonest reactive elements in the universe. You get them together, and you're going to get some
natural affinity for each other. Is that what
Yeah, they're both very reactive. Yeah, and it's the same with your ammonia ice, which is NH3. Once again, it's your hydrogen. And what's after oxygen? Nitrogen. So nitrogen reacts with hydrogen, and then your methane, your carbon reacts with hydrogen, which is CH4. And so you've got your three most commonest elements short of hydrogen. They all combine with hydrogen to form those ices. Yeah. So yeah.
Even, I was going to say, even rocks have a lot of oxygen because they're mostly silicates,
Yep.
which is silicon dioxide, and a lot of other minerals have oxygen involved. Just because there's so much oxygen, it reacts with anything it can, basically.
Yep. So it is a natural thing to happen. Yeah.
Just another question. So a number of years ago, there was a lot of interest in Titan.
Yes.
Other than proximity, what would be the reason for exploring Europa more than, let's say, Titan?
So what is why explore Europa before Titan? Was a lot of there is a lot of interest in Titan. Probably a couple of comments here. A lot of interest in Titan, and indeed there is a mission planned, Dragonfly mission to Titan. So that will come. And some people ask the question, why Europa versus Enceladus? Because Enceladus, one of the moons around Saturn, has got the evidence suggests from the Cassini spacecraft that it's got the plumes. It's got the ice shell with the subsurface ocean. Why Europa? Two reasons there, three reasons actually. One is that Europa's a heck of a lot closer, and easier to get to. Two is that Europa is a lot larger than Enceladus is a tiny, it's a relatively small moon. So Europa's a lot bigger, so you're going to have easier to study it and more water and so on. And the third reason is that by the time they discovered the plumes in Enceladus, let's go and investigate there. Well before then, Cassini had already spotted the plumes of water coming out of Europa. NASA had its conferences and decided and allocated time and prioritised Europa long before they discovered the plumes coming up from Enceladus. So, but in answer to your question about Titan, there is a plans to go to Titan in the future called the Dragonfly mission.
And what would be the purpose of that one?
Once again, looking for the conditions for life. Can it support life? If it does, is there life there? You've got all these methane lakes, ethane and methane lakes there. So is it life? If there is life there, how familiar is it? There's an atmosphere. It's about twice or 1.5. I think it's 1.5 times the density as our atmosphere. But it's a different atmosphere. It's full of nitrogen and hydrocarbons and so on. So Titan it has an atmosphere. There's a lot going for it. It has these lakes, albeit methane and ethane, but thick atmosphere. So there's a lot going to study Titan. And the answer is yes, there is a Dragonfly mission planned.
Enceladus, they're planning to send a probe in to drill through the surface.
I think at some point in time. Yeah, in due course, yeah. You never know these days with things getting cancelled and stuff. But yeah, you're quite right. The intent is to go to Enceladus and to go to Titan. Have a look on the Dragonfly mission to Titan, and it'll give you a lot of. They're talking about a submarine to actually go underwater. When I say underwater, I should say under fluid, under ethane and methane in the lakes. Yeah. Yeah.
With the radiation coming off Jupiter.
Yes.
Do we know how much radiation is that and how much?
Yes, yep. So some of the radiation in Jupiter, how much is it? It's very, very powerful. It's actually got three sources. The solar wind. Ironically, the largest source is actually from Io, spewing up. I think Jonathan talked about that last month. And the third one is some of the plasma coming up off Jupiter itself. But it's very powerful, as I mentioned, just the radiation belts that Europa travels through. Exposure is 5.4 Cepherts, not millisieverts per 24 hours. Now that's a huge amount of radiation. For example, 3 chest X-rays is 1 millisievert. And here you're talking 5.4 Cepherts. in 24 hours. So intense radiation. Instruments, some of the instruments were damaged in Galileo. Galileo was not primarily to look at Europa, it was primarily to look at Jupiter. But yes, it did get some of its instruments fried. So that's why the two reasons they have the big titanium aluminium vault for the instruments, and they only spend a short time going around Europa before they head back out again. For it is intense electronic damaging radiation. Does that answer your question? Yeah. Yep. So I think that's probably... oh, you got one last question? No. Oh, yeah, I think that should wrap it up. All right, drive home safely. People, if you can still find your car out there. Yeah. Thank you.